And don't use the lifts. Don't use the lifts. If you do need the lift, then please wait for one of the QMH staff and they'll help you. Okay. Okay. Now moving on. Now, normality means that we have minutes from the previous meeting, which the minutes taker reads out, and we all accept them. But whilst we've been having the meetings on Zoom and things like that, we haven't been doing it that way. So council, when we have a council meeting, which we do on a regular basis about every 4 to 6 weeks, we check the minutes, and if they're okay, then we do ratify them. So what I can say is that the minutes have been ratified by council. They'll be in draft form, and Phil Williams, the minutes taker, will send them to me. I'll sign them, and then he'll print them off for the record. And if anybody wishes to see any of the previous monthly meeting minutes, then see me or any of the council members, and you can have a look at them. Okay, thanks. Apologies for absence. I've got a few apologies for absence. So we've got a few so far, Mark. I've got Dave Whittle, Kate Betley, Hilary Harper, Colin Murray, David Harper, Chris Banks, John McCombs, Zoltan Gregus. Do we have any more, Mark? Yeah.
Well, Colin Murray's there.
Right. Okay, good. Okay. So I mean, for the minutes, we'll need to update those, and all the apologies for absence will be in the minutes of the so that we can read them out next time. Okay. Okay. Moving on to the next item, which is announcements, and I've got some very bad news. Firstly, I'm sorry to have to announce the death after a long illness of Jeff Regan earlier this month. Jeff was a great ambassador for our society. He was a very knowledgeable amateur astronomer and a highly respected member of our society. He was a good friend and colleague to many of us within the society, and he will be sorely missed. Our thoughts are with Beverly, his wife, and family at this very sad time. I have the funeral arrangement details. If anybody wants them, come see me later. Okay, so we'll now have a minute's silence in memory of Jeff Regan.
What is it? Clara, phase 2. Color coordinated magnet.
Thank you. Okay, moving on to some other announcements. The newsletter is out. You should all receive an email that the newsletter is out on how to access it. If you need to know how to get to it, it's on our website page. It's on the home page at the top. You'll see a little that you click on. It says newsletter. Jodrell Bank is reopening. The visitor centre attraction is reopening after a £21.5 million refurbishment. So I suppose it's going to be very good. It opens on the 4th of June. Tomorrow, the 19th of March, is the Practical Astronomy Show at Kettering Conference Centre. If anybody didn't know, then yeah, Kettering tomorrow. One more thing for me to say, and that is that there's a temporary change to council. Noel Rimmer has stepped down from council, and Hilary Harper has temporarily taken his place. Hilary will become the librarian until the AGM in May, when everybody gets voted in again, or not. So plus we are at that time again when we ask, would any members who qualify, and to qualify, you have to have been a paying member for 12 months previously. Is anybody interested in joining council and help run the society? We do need you blood. You know, we are looking for people. Yeah, it is a little bit of a time out your life, but it's also, you know, really, really good because you get very involved in the society and the running of it as well. And there's a few little perks because you find out things before everybody else as well. Anybody interested, please contact Mark Galvin or our secretary or any of the council members, which is me or Dave. We're a bit short on council members tonight. Anybody got any more announcements? Yeah, of course. Yeah. Oh, yeah. Okay. So, Mark. Yeah.
So as Steve was mentioning before, there's the mailing list where you can get the newsletter and information about, you know, meeting invites, things like that. Could you make sure that if you have signed up for it in the past, or if you're a member, that we've got up-to-date contact details for you? We did a little test the other day on it, and out of about 350 people on the mailing list, 83 of them haven't opened a single email from us. They may not have even received it in at least 6 months. And that includes some members as well who've been missing invites and updates. So if you could just make sure that we've got up-to-date info for you and phone numbers as well, if you remember. Thank you.
Thank you. Thank you. Okay, I'm going to ask Dave just to give us an update about Pexhill. There's a few things he wants to talk about there. So I'll just move out of the way. Thanks, Dave.
Okay, hopefully everyone can hear me. Just a quick update. I'd reported previously that we'd had roof leaks at the observatory underneath the dome, and it was a drip, drip, drip at one point. And then with the recent winds, the gales that we had, the water just started coming in bad. It's damaged some of the ceiling, and at one point it was coming in on the electrics. So that was a bit of a concern. We've been up there since, myself and John McComb's been up on the roof, and we've sealed everywhere we can. And it's looking good. For the last 2 weeks, despite all the rain we've had, it's bone dry. That means now we've got to do a bit of repair work on the ceiling, a bit more decorating, and also cleaning all the dust up that's accumulated. Flies, you know about, we had the infestation of flies. We've got past that stage, so that's good news. Just moving on, regarding the reopening of the observatory, we're getting there, and that's a positive note. We had intended this month notifying all the membership that we'd take maybe the first 30 members and issue a virtual ticket, and basically the first come, first served. Due to technicalities and roof leaks, we've not been able to do that. I asked permission from council, and council agreed that I could have a small group up there in a quick turnaround. So on Wednesday, I did a quick call around messages out to the ones who generally go on a Wednesday evening, and 10 people attended. I believe Liverpool were playing that night as well, so this does affect figures. So 10 people attended. They all agreed that they want to get back, and other people who couldn't attend on that night want to get back as well. And they're all happy to follow any guidelines that we put in place regarding COVID restrictions, social distancing and so on. And it gives us a chance then maybe to, before this summer comes in, we can meet back up there on a regular basis. But at the moment, we're just trying it on a one-off, feedback to council, let council discuss, and then maybe we'll open once every fortnight. I do have a group of night class coming up, and that's still ready for that. Okay, Paul? I think is that enough? I think. Any questions? Yeah. That's good. I like that.
Checking your emails because we will announce.
I think that's the way it is, Steve. Yeah.
The next opportunity to open up this should be very soon.
Thanks very much, everyone. Thanks.
Thanks, Dave. Right, and can I just say that when Everton are playing at home, we usually have more people attending. Okay, so normally at this point we have new members, and we have got about 70 people asked to join the society. So if you're watching on Zoom, come to the next monthly meeting and we'll sign you up. It's free at the moment. You don't have to pay anything until September. So please do come. And we were expecting somebody tonight, but never mind. So if any of the guests want to join, there's some membership forms outside as well. So see me later. Okay, thanks. Right, okay. On to the main thing for tonight. And I'd like to welcome Dr. Luke Hart, who is, well, I'm not quite sure. So I'm going to hand over to you, Luke, and you can tell us about yourself, what you do, and what your talk's all about. So thank you very much. And here's Luke.
I don't blame you for not knowing what I do, because I don't even know what I do half the time. Yeah, so my name's Luke. I was at University of Manchester as a student from 2012 to 2016. I was a PhD student from 2016 to 2020, and during the pandemic, I was a postdoctoral researcher within the cosmology group. Recently, it's probably the wrong forum to say this, but just sort of the job market for astronomers and particularly physicists right now is not as amazing as you'd really want it to be. So unfortunately, I've had to take a dive into a new industry, but I'm looking at software and analysis to do with renewables. So I feel like I'm doing something positive. But let's park that, because the real reason why I'm here is because I've spent over 5 years of my life. I think the right word, Emma, is obsessed with the cosmic microwave background and all the physics that goes on within it. And therefore I feel not necessarily qualified, but I believe the obsession gives me the credence to talk to you about it. And hopefully we can get something out of this. So yeah, I want to talk to you about the microwave background. I want to talk to you about what it's all about. I want to talk to you about why it's such a big deal, if you didn't know already. And you know what, let me just, yeah, that was supposed to be a fancy spinning globe that started off the talk, but I forgot the animation. Let me just dive straight into the overview. So first things first, I want everyone to have a really good idea of what the history of the cosmic microwave. Oh, wow. That is. No worries. Yeah. Thanks, Mark. Yeah. Keeping me on my toes. Good. So there'll be a few animations in here because I was a drama kid, right? So I like a little bit of suspense and animation, right? But I'm really sorry for those of you tuning in on Zoom, because obviously you're not going to be able to see these little things. So I really do apologize, but also sort of passive aggressively, this is where Steve says, yeah, you should have come in person. But no, anyway, joking aside, thank you ever so much, anyone on Zoom. And I please don't turn off. Yeah, so just a little word of warning there. I think Mark's going to absolutely do a cracking job at keeping up. He doesn't look so convinced, but yeah, anyway, so I'm going to start off talking about the history of the microwave background, because I think the story of how it was discovered is incredible. It was a complete fluke. Then I'm going to describe a little bit of a framework of cosmology for you, which centers around how we look back, essentially, if you didn't know already. To those of you who are already familiar with the phenomenon of redshift in the audience, you're all going to be bored stupid by that particular set of slides. But I feel like we need to get our feet on the ground before we proceed. Then I'm going to explain to you what exactly this CMB thing is all about. And I'm going to give you a beginner's guide to studying it, so you at least know why all these cosmologists are so obsessed with it, and why it's such an important facet of our standard model, our standard understanding of how the Big Bang Theory worked, and why the Big Bang Theory relies on the CMB being there. Then I'm going to talk about, as a wrap-in of that, I'm going to talk about this thing where I colloquially refer to this as a recipe for the universe, how the universe really depends on sort of features of the CMB, and where we're going to go from there. And then I believe we're all going to take a break, which is great because I'll need to catch my breath. And then I'll explain the journey of how we've actually been able to detect and do some real proper science with it. And that will sort of be like a flying tour of some telescopes. Then I'd like to talk to you, I'd like to blow my own trumpet a little bit about some work we've done in Manchester with regards to this topic, because there's nothing I'm an expert in, if not the stuff that I've been sat there doing day-to-day work on. And finally, I'm going to talk to you about this thing called spectral distortions, because this is something you're going to hear about in the media. It's going to hear about in the news in the next 10 to 20 years, and it's going to really revolutionize everything we thought we knew about the universe. The reason why you haven't heard about it yet is because we can't detect them, spoiler alert. but we will, and when we will, they will change everything. And then finally, I'll conclude, and I'd like to finish off by just saying, I'd like to get through this as quickly as possible, because what I'd rather hear from is you. I'm really more interested in all your questions. This is the first time I've ever spoken properly to an astronomical society before. My only other dealings with any astronomical society before has been the Royal Astronomical Society, and it's been all of their editors giving me a really hard time when I've been publishing papers. So it's much nicer to speak to you guys in person, people who are really passionate about the study. Much friendlier, right? Yeah, don't tell them I said that. Okay. No, it's okay. They already know. Trust me, exchanges says all. Anyway, let's go through the history. Something in the air. Yeah. So the history of CMB actually starts from very, very humble beginnings. And it starts with these two scientists in America called Arno Penzias and Robert Wilson. Now, if you heard the story, this is going to be a bit boring. But they actually were tasked with, by several companies, particularly the company they worked at in Bell Labs in Princeton in New Jersey. They were actually trying to work out how to get rid of all of the guff, all of the gunk in their radio signals, where they were trying to calibrate radar that could be sent between balloon satellites and Earth. And this is the Holmdel antenna that they developed with that. That's them at the site. And that's another bigger picture of it. And yeah, they removed as many foregroundy signals as they could muster. They did a lot of analysis to understand what the radio astronomy contaminants would imply. And even after they did all of this, they still got this little signal, this really annoying, noisy signal of about 3.5 Kelvin. Now, obviously 0 Kelvin's as cold as we can go. And the 3.5 Kelvin was a bit of a stickler for them. And I've put a picture of a pigeon. Does anybody know? Let's have a little bit of audience participation. Does anyone know why I've put a picture of a pigeon? Does anyone know? Yeah, it's because it's exactly right. Pigeon poo. Yeah. So what they actually thought the signal was, they thought, oh, maybe it's just the fact that the pigeons have just gone number 2 on the receivers. So they literally considered everything to try and work out what the signal is. So yeah, we're going to park it with Penzias and Wilson for a second here, and I'm going to take you somewhere a little bit more theoretical. So another thing that was going on at the same time, another sort of discussion, is the idea of where we come from, where our universe begins, how's it going to end up, model of cosmology, shall we say. And if any of you, if I do damage to this and you don't understand what I'm talking about, can you please, I would honestly refer Cosmos by Carl Sagan. It's such a cliche, but this book really got me into cosmology in the first place. I absolutely love it. It's what set me off on the path and literally didn't look back. And so the base, when Carl Sagan talks about a lot of things in astrophysics, but when he starts talking about cosmology and he gets to sort of the last 100 years, it's all about these two models. It's about the steady state and the Big Bang. And you had a group of astrophysicists, a group of theoretical physicists in Cambridge University, led by the late, the great Fred Hoyle, who all believed that there was too much, there was too many theoretical groundings, there was too much coincidences for there to be a Big Bang. I think there are certain arguments to maintain that Fred Hoyle was very sort of skeptic many physicists believe in this idea of the universe coming from a point. George Gamow, who is the German physicist, you might have to correct me on that, but he was working in Germany at the time. He was a very eccentric astrophysicist who believed in the Big Bang Theory, really got it off the ground. And sort of foundational work led by Georges Lemaitre, who was a French priest who fundamentally believed in the Big Bang Theory, and observations, which I'll go into in a second, from Edwin Hubble. They believed that the universe sort of came from a point. Even Albert Einstein tried, he didn't like the Big Bang Theory at first. He thought it was a bit, pie in the sky and that. But then when he started to reconcile it with his own ideas of general relativity, it really didn't go well with this model. So he sort of was a dipso facto member of the Big Bang group, but he didn't really, Albert Einstein was famously skeptical of things that weren't absolutely sturdy. So you've got these teams forming of these physicists, these proper very, very adversarial style, competitive style, as is everything in physics. So everything's expanding constantly in a steady state, and everything's getting sparser as the world gets bigger. By world, I mean universe, okay? That's the Big Bang Theory. So now let's just click back. Why on earth am I talking about a horn antenna, the Big Bang Theory, and pigeons? Where do they all come in? How do they all link together? Well, it actually turns out that at about the same time as Penzias and Wilson discovered this weird anomalous signal on their telescopes that they couldn't even put down to pigeon poo, there was a group literally just across the road, Dickey and Wilkinson et al. They were working on a consequential theory coming out of the Big Bang, and one of the consequences of their theory was this relic radiation. I think that's actually what they. So there are other papers by which I will talk to if anyone wants to discuss about Russian physicists Yakov Seldovich and Rashid Sonyaev, where they discuss this relic radiation. And you'll see Jim Peebles' name there. Notably, you'll know if you follow popular, Jim Peebles recently won the Nobel Prize. These are all people who were very, very, very tantamount to this discovery of regards to this theory. And what they realized, is that this excessive noise temperature really can come as a relic of the Big Bang Theory. And so if you apply lots of maths in this big burst of radiation, they said, well, where is it? And obviously at the same time, Penzias and Wilson had published that this spectral signal was coming out in the as a result of temperature. And they actually consulted with Dickey and Wilkinson. They paid them all the right homage. They gave them all the credibility for the theory and everything, just most respectable physicists as you can be. And it was Penzias and Wilson who won the Nobel Prize. They won the Nobel Prize for this discovery. And even they've said in popular magazines and things, it was an accidental discovery for the discovery of the CMB, which they literally were just testing for radar on balloon satellites, and this is where it came from. And it gives us this incredible there are lots of ways that this could be and couldn't be wrong at the time, but this sort of arose from a very, very keen understanding. Lots of people were like, yep, that's got to be quite a strong contender for the Big Bang Theory. Now, the fact that we have this relic radiation that's just dispersed, and as it's dispersed, that must mean density is getting sparser. And then you go backwards, and that's where the Big Bang sort of stands with this signal. So that's the history. And before we go any further, I think when we talk about cosmology, everything relies on the fact that you understand what we mean when we say we look back, even this phrase looking back in time sounds a little bit sort of wishy-washy, Doctor Who. And there's foundational physics to that. So this is a terribly edited picture of someone looking at a galaxy, right? And that galaxy hasn't been edited very well, but it is supposed to be like in the middle of the color spectrum, like a yellowy orange, okay? And when you look at a galaxy in the sky, and you'll see the light coming from it, you can obviously measure the spectrum of the light, the frequency of the light coming from that, and that's the basic principle of spectrometry, which is a popular sort of method of detecting things in astrophysics. However, if you look at this galaxy and because you expect it to have certain elements, certain atoms, their properties, and all of the frequency has actually been shifted to the longer wavelengths, or shall we say the red end of the spectrum, What that actually means is it's a light equivalent of something we call the Doppler effect, which is, you all have noticed, if you ever stand next to a car going past on the road, as it comes towards you, you will, if it like toots its horn, the pitch will be higher towards you and it will get lower as it goes away from you. You're like, yeah, that is the Doppler effect. Okay. And because light and sound are both treated as waves, you can apply the same logic to sound as you can to light. And so this is literally what astrophysicists do when they are measuring galaxies to work out how fast they are moving away, or how close they are, fast they're moving towards you. I'm not going to put up the equations because that will go down a rabbit hole. But just take my word for it that that's the sort of equivalence that we apply, and you can actually calculate exactly how fast that galaxy is moving away or towards you. Similarly, when we see these galaxies moving towards us, the light is shifted to the higher end, the higher frequency end of the spectrum, and that's why we call them blue shifted. So that's really important, because actually when we look at objects further and further and further and further away, we don't really know how to make an implicit assumption about when they were created. If you look up in the sky, everything sort of looks roughly the same to the naked eye. You'd think, well, that star and that star are sort of the same brightness and what have you. And it's really complicated to work out how far away they are. But there's another level of complexity to this, and it was discovered by a man named, or I would say discovered and proposed by a man named Edwin Hubble, who is probably one of my favorite figures in science. I absolutely love the work he did, because it's tantamount to modern cosmology, where he looked at how galaxies were redshifted as he worked out sort of how far away they were. So if you take galaxies, you can understand how big they are based on their angular size on the sky. And then you can measure the redshift by how the color of the light has changed based on what type of galaxy you're looking at. So galaxies in specific classifications tend to all look the same. They have the same atoms present on mass. So when you see these redshifts, it's very clear to pick out how far away and how fast they're moving away. And that's sort of what Edwin Hubble did. This is a 1930 paper. This is one of his most famous papers. And he noticed this direct correlation, which summarizes that the further a galaxy is away, the faster it's moving away from us. And that really was quite a smoking gun for people who believed in the Big Bang Theory. That really was the thing that piqued their interest, got everybody rolling, thinking, oh my goodness. And that sort of really was the ready, set, go for the cosmology of the last 100 years. And yeah, so that's a really key thing that we look at, because sometimes in cosmology, we actually talk about things in redshift rather than in distance or things like that. And so forgive me if in the next few slides, I slip between how long it was after the Big Bang or what we call the redshift, but that's why we say that. So, and that's how we measure how far away things are, or particularly how early they were close to the Big Bang. So when we look actually into the past, and this is a very popular graphic developed by the Planck team. Planck was a satellite developed by the European Space Agency. We have all of these sort of little areas of cosmology happening as a function of time, where the left is the Big Bang and the right is today. And you're gonna, and don't worry, because I still have this moment as well, as everything starts to look less and less and less familiar as you go to the left. So we've got the solar system here, we're obviously aware of, galaxies we're aware of, and even galaxy clusters we see and we can detect now. But eventually we get to a point where galaxies started evolving, and I'm sure you've heard people come in and to the Astronomical Society and talk about galaxy formation. You may have heard, I don't know, because I'm not an ardent member, as it were, but you might have had talks about a phenomenon called reionization, which is the process when the very first stars were generated. This sort of happened, say, about 1 billion to this sort of happened between 100 million and 1 billion years after the Big Bang. And eventually you go back and all of these different phases happen back to the Big Bang. And as we write time on the bottom here, we can actually write redshift, which gets larger and larger and larger and larger as you go to the Big Bang. And in fact, the Big Bang would actually theoretically mean an infinite redshift, okay, in algebraic terms. And so the first ripples, shall we say, the first time someone flicked a pebble into the ocean of the universe at the Big Bang were seeded literally here. Like you can see that's 10 to the minus 32, 0.32 zeros and a 1 seconds after the Big Bang with those first ripples. Like I can't get my head around that. But then even though that's where the ripples happened, this is where what we call the cosmic microwave background radiation was, shall we say, made or produced. Because I want to just get a bit funny when you talk about the CMB being made, because it was always there. But no, the actual production of a light that shone out across the universe was here around 380,000 years after the Big Bang. So you flip that background, what's that? 13.7 billion years minus 308. I mean, this is very, very close to the beginning of what we call time. Okay, so I still can't get my head around this. So, but yeah. So let's go through the actual what is the CMB, what's its purpose, why are we interested in it, and then finally we'll go into the sort of what you can do with the science of it. And there are multiple ways you can go with this. So the sort of elevator pitch explanation of it is, I'd say, it is a relic radiation that is left over from the Big Bang, from those ripples that happened just after the Big Bang, caused sort of some places to sort of clump and some other places to sort of sparse. And that actually gets seeded right into the very first light that was turned on in the universe. And that has turned to microwaves, because as the light has gone out over 13.8 billion years, that light has got cooler and cooler and cooler. And so you can only imagine how hot that light must have been in that instant. But now we're talking, it's very, very close. I mean, it is only a couple of Kelvin, and it's very, very cool microwave light. And a really interesting feature of the CMB, if you might have heard of this before, but if you turn on one of those sort of if you turn on an analog television and you don't get any signal from it or anything like that, the background signal that you're picking up on the television is the CMB. And even if you wipe out all of the radio signals that could be coming into your receiver on your television and you get rid of everything you possibly can, you will still find that background signal, because it comes from every single distance instantaneously. It's just so weak and so low energy, it doesn't really change our day-to-day life. But it's here, it's everywhere, and it's one of the main fun. When we look at the sky, we see something like this, which actually is the microwave signal. But what we've done is we've taken off that, say, 3 Kelvin. So this is the difference from the roughly 3 Kelvin signal that was seen by Penzias and Wilson. A little bit more precise now, because obviously WMAP was 2001. And these are the slight temperature deviations that we see across the sky, but we still see those microwaves coming from every direction on the sky. And obviously this has been made to filter out the galaxy, because the Milky Way would probably by and large ruin this picture if we had it real time, because the galaxy gives off quite a lot of microwave emission. But if you take out, subtract that galactic signal, you get something that looks a little bit like this. And yeah, as you can see, it's kind of interesting. For those of you who aren't aware, this is what we've done here is somewhat like a projection, similar to what you would do with an Earth map. You actually have projected a 3-dimensional look at the entire sky onto a 2-dimensional plane here. So this is the entire sky, just as best as you can visualize it in 2 dimensions. I'd have to have like a hologram or something like floating in the room for you to see it properly, like as if we were looking out at the sky. But yeah, this is the image that WMAP took. And then it got a little bit better. You can notice here, I don't know if you can, but I certainly can. The sort of precision on those differences got a little bit better here. And that's the product of ESA's work from 2013, 2015, 2018, their slow releases of what they did to measure the cosmic microwave background temperature. I got a bit ahead of myself here, so I talked to you about some new emissions. This is a mission called COBE FIRAS. This was launched by NASA in the 1990s, and this was the very first way we ever measured the CMB's sort of different temperatures across the sky, rather than just getting that one prevailing signal Penzias and Wilson got in the 1960s. And this, I I'm loath because I'm terrified if no one else is on my page here, but does anyone know what's so important about this shape here? It's a physics question. Bang. Oh, awesome. I'm so happy. People, right. So yeah. So do you fancy a go at explaining what a black body is? It's okay if you don't, I can explain it. No, okay, cool. Okay, so a black body in thermal terms is something that emits about as much as it sort of absorbs in radiation. It's a perfect emitter of radiation, and it follows this spectrum, which in physics is very, very, if you're a physicist, you can sort of catch it by eye. It's something called the Planckian spectrum. It was something that Max Planck was one of the first people to sort of understand that radiation follows. And so when people saw this, they were like, holy hell, there's this black body signal coming from space, and this relic radiation follows it. And what you can do is you can find the peak of this curve. And when you find the peak of this curve, you can change using mathematics, the frequency, the rough frequency you're measuring using algebra into the temperature for the CMB. And that was the value they came up with. It was, in fact, I'm jumping ahead of myself. That value I'm going to explain in a little bit more detail down here. But yeah, that's 2.725 Kelvin. And to be able to measure this signal, they obviously had to take it as a function of frequency. So this movie shows you what that map looked at different frequencies. And you can see the Milky Way is in the middle there, and all these different frequencies of light coming in. And these little things are pixels, which measure a temperature. And if it's blue, it's less than the average temperature. And if it's red, it's more than. And so you sort of do some fancy mathematics, which I'll explain in a later slide, but not with equations. And you can work out and calculate the intensity of all these different frequencies of light. And yeah, they measured it down to, I mean, obviously you can see that says 2.725, but this is the preliminary estimate that came out of the paper that they did. This is an updated figure when they changed the data analysis. So yeah, this is sort of incredible, especially more importantly for, as a physicist, I look at this and go, wow, that error bar is really attractive. And that 0.002 is really, really awesome. And yeah, this ambient light is coming in from all directions, roughly the same temperature, and follows this spectrum no matter where on the sky you're taking the signal from. And I don't really want to go into it in this talk because I'm conscious of how much time I can spend talking on all these things. But some two principles we take when we, as cosmologists, try and do some proposals and theories for how the universe would behave under Big Bang conditions is homogeneity and isotropy. And they're just fancy words for saying, if I picked you up and put you anywhere in the universe, you'd look at the sky and roughly see the same thing. And the isotropy means if you looked at any direction on the sky, you'd see roughly the same thing. Those are just two fancy words for that. But this sort of gave credence to that and the fact that they made these assumptions. Now, I doubt even the eagle-eyed of you could notice that actually, if you look at this curve there, because it's just not precise enough, the resolution, there is actually a very, very faint little wiggle on this curve, even though it looks like perfectly smooth. And I'm not even sure if it is actually naked to the eye, but there is a little wiggle on this curve. I'm not going to talk about that now. I'll come back to that right at the end of my talk, but I want you to just keep in mind that actually this perfect signal is not so perfect as we initially believed. Okay, so you want to study the CMB, you want to understand why the hell everyone's so obsessed with it. Where can we go? It just looks like, okay, cool, we've got this good signal from the sky, it looks great, we've got the temperature, but what's the big deal? Well, if I take the Planck map, for example, this is a full sky survey of the cosmic microwave background. You would definitely be forgiven for thinking, why would you bother going into this much detail if you already had a measurement of the temperature to 1 in 10,000, 1 in 3,000, I wrote it out, yeah. So that temperature signal, we had the error at 1 in 3,000 accuracy. That's pretty good, right? So why would you need to keep doing this? Well, the reason why is because after COBE FIRAS came, WMAP and Planck, these NASA and ESA missions that came in 2001 and 2012 respectively, they actually tried to do something entirely different. Rather than measuring the temperature, they were actually interested in what the difference in the temperature could tell us. And that might sound a little trivial, but this comes back to the theme of the talk. The title of the talk is about ripples in the Big Bang. And the answer, as always, lies in the data. Okay, so if I heard this again, a PhD gives me flashbacks, right? So Okay. So if you measure the temperature of every little spot on the CMB, obviously I've told you before, the red sort of roughly means hot and the blue means cold, above and below an average temperature. So what this mission actually did was it would take 2 spots on the sky, measure the difference in their temperature. And I really simplified it. If people are watching who were part of Planck, they'll be horrified at my explanation. But then they would measure the size of this ruler. So they would measure the distance between it and check the difference in temperature. And they do this thousands and thousands and thousands and thousands of times for all of the possible different perturbations in the sky. And yeah, from doing that, using some very, very, very clever mathematics, which have been studied over the past sort of say 50 years, they can then create something that effectively tells you how strong the change is, as if you counted all of these differences and you added them all up. This is a very layman's term. I'm sorry if I'm having a butcher of explaining this. If you added it all up, how strong would that particular correlation at that particular sized ruler be? And when you change that into something that looks a bit more like a plot, it looks like this. So this is a graph. This is a very, very, very famous graph, especially since Planck did it, of how strong the temperature deviation or fluctuation, as they call it here, is as a function of angular scale. And you can just, angular scale is a bit of a fancy word for saying how big the ruler is. Okay, officially, because it's on a sphere, you have to call it an angular scale because you're technically looking at the angles, right? But it literally is just how big or small that particular ruler size was. They said, right, this is the ruler size, added up the possible configurations of all those different temperature deviations, and say it was about 1 degree big, like say this big, they would then say, right, okay, that's the strength of those temperature fluctuations. And just to give you some power to how well we think we've got the Big Bang on point and how we think the model lambda CDM is, the green curve is a theory curve. So the green curve is the theory curve that cosmologists have come up with for the best fit model of what actually composes our universe. And the red is the data. And I mean, you know, you can do statistical measurements and analysis and stuff, but I don't know of any single graph plot of data in the whole of astrophysics that fits as well as this. This is like this made the case for all cosmologists for why they should get money to do what they do. Okay. And it really is quite a unique shape, and all of these little features and all these little things have a different effect. If they were different, what would happen to the universe? And that's where we start to get into the value of the CMB. I'm going to make a little comment on that big blob of green there. That's where the error bars have really jumped up. And the reason for that is, again, I'm sorry, I'm just a sucker for interactivity. Could anyone potentially try and explain to me, this is an angular scale, yeah? So this is how big or small the ruler is. So a little clue is, as you get higher on this scale, the ruler gets smaller and smaller and smaller and smaller. So could someone potentially throw a reason out as to why, as I get to a bigger and bigger and bigger and bigger ruler, eventually the error just starts going up? Does anyone know? Yeah. 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 So geometrically, you might not be far off, but that wouldn't be how I would explain it from the data perspective. But I don't think you're far off. Does anyone else have a rough idea? I'm sorry, it's just like, I'd much rather you do the work for me. So when we start measuring temperature deviations at very, very far distances, eventually you're going to get to a point where, if you think about it, how the hell is a telescope going to measure a temperature deviation from one direction, as opposed to physically, how is its telescope going to get to a point where it can measure the temperature on the opposite side? Especially thinking ground telescopes, right? Ground telescopes can't do this at all. They have no chance because they immediately have more than half the sky cut off to them, right? But even the satellite ones, they can't actually physically take enough data, because if you remember, I said you add up all the possible rulers. Now, I should have brought it back, shouldn't I? Someone's got a very persistent alarm. So no, it's fine. It's fine. I'm joking. It's fine. So if you look here, if you look at the small rulers, if I took every little deviation across the sky for the small sized ruler, I could probably take almost an infinite seeming number of points across the sky of every pixel to pixel to pixel. Because don't forget, these are hitting, this is a physical problem. They are hitting pixels. The photons are hitting pixels, and you can't get infinite number of pixels. However, when I start making the ruler a particular size, eventually I can only get so many of those ruler point to point to point. And if you get anything, I know it sounds a lot, but if you get a data source of around, say, 100, even that sounds a lot, but it really doesn't actually statistically mean anything. The error is so large compared to when you do this and you say you have an angular size of, say, 0.1, and you've got like on order of potentially millions of data points. So this feature is called cosmic variance, and it's an error that we implicitly plop in because we say, no, actually, we can't get enough data at that scale. And so the error bars sort of start to jump up here. And there are missions that are trying to improve that, and there is a certain limit we can hit, which we can never get above. But yeah, sort of that's the explanation for that. And I hope I just wanted to explain it because it's a good way of visualizing everything. And this is sort of how you can think of how the sky alters when you look at these different ruler sizes. So I don't know if it's a helpful metaphor, but something I like to think of when I look at the CMB sky is actually the height of this graph is almost like how well focused the CMB is at these different ruler sizes. And as you look, it's very, very blurry, and then it sort of hits this prime, and then everything gets too fine again, it gets too granular. And that's sort of how you can imagine the CMB spectrum from. And this is a fantastic piece of learning tools provided by Professor Wayne Hu in the University of Chicago. I thoroughly recommend, if you're interested in what I'm talking about today, going away and looking at some of his animations. Yeah, so sorry to the people who are online, this is absolutely useless. I'm so sorry. But yeah, if you literally type in Wayne Hu, thank you. Cheers. If you type in Wayne Hu, University of Chicago, his website will come up, and links to the animations are dotted around his website. So it's a really good learning tool. It's how I learned about the CMB when I was an undergraduate. And these visualizations really do help. So yeah, so obviously there's a lot of mathematics and solving equations and things, and I started talking about how this was actually useful, but you could still be asking, and I would quite rightly assume, what is it good for? And that's where I come to the sort of pretentious slide called Recipe for a Universe. So when you are talking about a universe under the Big Bang Theory, what we call a lambda CDM universe, and I'll get onto that in a second, there are certain crucial ingredients you need, otherwise the Big Bang Theory doesn't really tend to work. And I'm going to try and explain them as sort of, this is sort of how I visualize them, so I hope it helps. So firstly, we need the ripples. So I talked to you about ripples from the Big Bang. We need everything. There need to be some bits that are a bit more clumpy than others. If that didn't happen, the whole of the universe would be like an undisturbed lake. There would be nothing on it. And as the universe grew, nothing would change and we wouldn't be here. So this doesn't fit any of our observables or the fact that we exist. So there needs to be some initial ripple, some initial disturbance. And that's what I mean by initial perturbations. Then we need matter. I mean, obviously we're all made of matter, and our stars are made of matter, and our planets are made of matter. And we need to be able to correlate what we see in the observable universe with what is there. And I pay particular homage to this term invisible matter, so-called, should we say, dark matter, and other things that we can't see with telescopes, and radiation isn't a thing for them. I'd love to talk, if anyone's got any questions about dark matter, I'm here all day, honestly. I love talking about dark matter. It's a very fascinating subject, but you need these things, and you actually need dark matter a hell of a lot more than you need matter that we're made of. Then you need something that actually drives the expansion, and that is my sort of free promotion to suggest to any of the members that if they like my lecture today, I'm happy to come back and do another one on what drives it, because that is a whole other kettle of fish. And you also need something that actually generates the stars. So even if you take all of these assumptions under the Big Bang Theory, everything would sort of just get more and more and more sparse over time. And this is where it comes back to that thing I mentioned at the start, regards to something that reionizes the atoms to generate the stars. And that is definitely required and is a very, very, very complicated piece of physics. And just as a smaller side, the worst thing about reionization, the kickstarting of the stars, is we have literally very little data to understand or explain that process. And that some of you might be aware of things like HERA, or the Square Kilometre Array, SKA. SKA is looking into a huge amount of development into how we can potentially better understand the process of reionization. So yeah, it's definitely required for your universe to resemble anything like we have today, and for the fit to be good. So all of that fancy animation can actually be described by, it's usually 6 parameters. I've added a 7th because there is a 7th one that I find quite important, but these 6 parameters are incredibly, incredibly important. So this actually tells, I'm not going to explain what these numbers are algebraically. I'm just going to explain it to you what they are phenomenologically. So NS, so probably easier to say AS is how big. If AS is bigger, it means I threw a bigger rock when I made the ripples at the start of the Big Bang. It means that the differences between the over and the under densities in the universe are much larger. And NS tells you the appropriate sort of, if you remember on the CMB, there was that massive peak. If I change NS, what I actually do is I change how sharply those ripples fall off as my ruler gets bigger. That's all those 2 parameters mean. And they quantify how big the fluctuations at the start of the universe are. Those 2 are by far the hardest to get your head around, because they even boil back into a theory called inflation, which is another thing that could take a whole one of these talks. These 2 are more, this is omega B means density of the baryons, and baryons are like the visible matter. It's everything we know from the observable universe. And omega C is C for cold, dark matter. And that's our invisible matter in the universe that we know has to be there. Lambda is colloquially what Albert Einstein referred to as his cosmological constant. This is his sort of botched job for how a universe expands. He sort of threw it in there because his equations didn't work under an expanding universe. But now we have come to adopt and love this symbol to mean dark energy. So you might have heard the phrase dark energy, this unbeknownst weird thing that pushes the universe and makes it expand faster. There is theoretical underpinnings to that. But as I said before, we are going to need another lecture and probably a bottle of wine to go through that one. And then H0 is Hubble's constant. It was named after Edwin Hubble. And it is, if you remember that curve, that straight line we had, sorry to you guys, it will be like that, right? Where the velocity and the distance are like correlated. You can think of Hubble's constant as the gradient of that curve. Okay, so it's basically how fast, how strong the expansion is. And it's something that is dominating the field of cosmology right now, because people who work at local, like what we call local astrophysical scales, and people who work on the CMB have a real big disagreement, and it is causing some big arguments. So yeah, that's why I've included it there. Those 2 sort of explain the expansion. And then this tau in physics is colloquially referred to as something called the optical depth. It's basically how far a particle can get through before it starts crashing into things in a particular system. And this tau actually tells us how strong the strength of reionization is, which would kickstart the stars, which would then affect the CMB. And you're saying, how would any of these affect the CMB? Well, courtesy of my thesis, like this. So this color bar tells you whatever particular parameter in the corner. This is a lot of information to ingest. Which parameter in the corner is here. And basically, if it's green, it means this parameter has gone very, very high. And if it's gone blue, it means this parameter has gone very, very low. And the reason why I've excluded this slide is to show you qualitatively how any parameter I change, it actually influences that spectrum I showed you that Planck, that WMAP have measured. And some of them have very like basic ways of changing the shape. Like you might have noticed that if you increase AS, the strength of the ripples, you get this massive, the cosmic microwave background basically gets amplified. So all of those differences just get larger and larger and larger. If you change the spectral index, NS, and you change at what point that the ruler becomes significant, right? This starts to, what happens is the CMB spectrum starts to tilt. Okay, so you get if you change it to a lower value, you will actually get the differences, which we call anisotropies. Okay, they will become larger at where the ruler is very, very big, and they will become smaller when the ruler becomes very, very small. Hubble's constant and anything that changes the expansion really just pushes the spectrum around, and you might, if you don't appreciate this, because this is something I spent a lot of time on my PhD on. What does that actually mean? Well, in essence, it means that the scale at which everything happens in the CMB has happened. It's almost like you've zoomed in. So if I increase Hubble's constant, it's like I've taken that image of the sky and I've sort of made a sub image in it, and then I've pretended that's my universe. So everything's ultra focused. That's how Hubble's constant changes it, and it effectively means, in a theoretical term, our universe is pretending that everything that happened in our universe happened at an earlier time. Then it's basically pretending that everything's happened faster than we think it has. And then the other three are sort of like a superposition. So for example, the baryons and the visible and the invisible matter change in very weird and wonderful ways. And that's good. That's what we want. You can either start testing crazy theories, like modified gravity as a theory where Einstein's theory was wrong or needed a bit of fudging. And you can test variations in that theory using the CMB. You can say there's a very, very weird particle in the standard particle model called a neutrino. You can change how many neutrinos you'd have. All these things change how the CMB behaves. And I don't want to go down those theoretical wormholes. But yes, so the main strength of this is now to say, right, well, we have a very, very precise measurement of these parameters. And so therefore, if we have a the spectrum. So if you have a very precise measurement of the spectrum, if these parameters change, they will drastically alter how that spectrum theoretically surmises. And so if you think of this backwards, when we get this could be to give us what the CMB looks like today. And that tells us how much visible matter there is in our universe, how much invisible matter there is in our universe, at what point did the stars reionize, how fast our universe is expanding, and how big were the ripples at the Big Bang. So it's really big, big, big information, and it basically shapes what we think the standard model of cosmology is. So to drop that bomb and walk away, I will end the first part of my talk there. After the break, I'm going to talk to you about the modern telescopes and where we're going with the CMB. I'd like to talk to you about a topic that I work on, which is about particularly the atoms and how it's very bright, in the CMB. And then I'll finish on some short discussion about the work that we've done in Manchester and these things called spectral distortions. So I hope this was okay, and thank you for listening to the first part. Thank you.
Thanks, Luke.
Brilliant. So you'll either be upset or relieved to hear that this is a much shorter part. But I think potentially, for me at least, this is the most exciting part, because this is sort of at the frontier now. So a lot of the things I've explained to you have been with regards to where the CMB came from, how we study it, sort of practicalities and things. Whereas what I'm going to talk to you about now is sort of the actual application and how we literally going from how we have physically got data on it to where we're going with the data. I want to talk to you about probably thinking, well, why on earth have you written that? I mean, that does seems like a really weird statement, but actually the relationship between the light in the early universe and the atoms is a really, really, really important, intimate one. And it is the crux of all the work that I spent doing in Manchester as a PhD and a postdoc, especially. And then I'm going to talk to you about these things, these spectral distortions, which I, for this lecture, have come up with the imaginative term of ripples upon ripples, because that really is what they are. If we think of the CMB as a ripple, this is actually sort of the second order on top of that. And then obviously I'll close by wrapping it all up and take as many questions as you can field. So let's start off with the telescope side of things, because I assume some of you might be really interested in some of the telescopes used to detect this. So the first big one that really started to shape it, I've already mentioned it several times, was WMAP. And it's called the Wilkinson Microwave Anisotropy Probe, and it was named after Professor Wilkinson from Princeton, who I spoke to you about, who was part of this team who developed the theory that actually coincidentally predicted the CMB as it was being discovered. And that's who he's named after. It's again, this is for people who are interested, but this is a really fascinating sort of telescope where they mounted these reflective mirror Gregorians, and specifically the receivers were tailored to be radiometers, and they would measure the two beams onto the two discs, and then they would measure the difference between them, and that's where you get this temperature difference measurement thing that I was talking to you about. You're gonna probably, I think I might have mentioned it on the Planck slide as well, which is coming after this. But low temperature physics and low temperature astrophysics is something that is incredibly important to the CMB. If you think about a signal coming from space that is a couple of Kelvin in intensity, then you need to have detectors that can deal with the noise to that level, because if you can't deal with thermal noise to that level, then your CMB signal is going to disappear amongst the noise. So the basic way to do that is to keep things as cold as physically possible. And we are living in an age where we can keep things down to sub-Kelvin, millikelvin now. WMAP sort of era time of things, this was down to the sub-Kelvin, I believe, maybe even the sub-centi-Kelvin regime. And they dealt with the majority of the sun's rays by having these pretty awesome looking solar panels mounted across literally everywhere on the instrument. And the detectors were literally kept constantly away from the sun. So it was always pointing away from the sun while it was doing all of its scans, even with the consequences of the taking out the Milky Way, taking out the Earth, everything like that. It was always pointing away from the sun, because then the solar panels could literally deal with all of that extra radiation and never sort of contaminate the low temperature receivers that were going on in here. It determined the age. It was the first thing that really truly determined the age of the universe to be 13.77 billion years. So when you hear the phrase 13.7 billion years tossed about for the age of the universe, the first time we ever came close to that figure as a precise figure was through WMAP. Yeah, I said that to you, like never had a telescope got that such precision. This was developed by NASA, so you know what's coming. ESA had to respond. The European Space Agency loved to one-up NASA on these things. They like to go toe for toe for each other on these big space missions, and Planck was no exception. The proposals for Planck were already in the paperwork whilst WMAP was scanning. So ESA were really very keen to try and do a better job. They pioneered this method of using bolometric detectors. So what would happen is the photons, you'd have these photovoltaic cells similar to what you have with your solar panels, really, but they were tiny, like sort of pixelated tiny ones. And they would measure the photons coming in. They would measure the bolometric sensors would measure the temperature directly from how they would actually kick and cause an electrical signal within that photovoltaic cell. And judging from where the telescope was pointing and the position of that particular cell, they could immediately project where that photon was coming from on the sky. So it was like basically unparamounted precision. And the pixelation that they got on these sensors and the data analysis therefore was, as you saw from the maps, sort of like an order of magnitude finer than WMAP, and it's because of some technology like this. The helium dilution then went down to 1/10 of a Kelvin. I believe that in one of the subsequent analysis, when they did a survey back in 2015, 2018, the team that were on this then started work on a satellite I'm going to talk to you about in a second, where we have got down to millikelvin. But in all intent, yeah, so this is about, this is 100 millikelvin. But this was better than, yeah, sorry, that was just saying that it was better than the detections at the time. But the take home is that this was the most precise calculation and most precise measurement of the cosmological parameters to date in 2013, but more importantly, 2018, when they did their full data release. They got everything out of it, and they'd had these astrophysics data scientists working on this for, or these data engineers who were working for astrophysics missions, who had been doing this for sort of 7 years. They got everything they could out of all of this data that the Planck satellite had been throwing out, as far as all the 2013 data. And this sort of gave us like a new level of understanding of how these parameters were. And the really nice thing was that WMAP measured this in a completely different way to how Planck did. And the agreement between them on most things was unbelievable. There is a couple of things where the error bars on WMAP gave a bit of a conflict, and that's still something that drives some of the cosmological study in our field today. But yeah, we were I mean, not I say we because this wasn't my work, but the people who were involved, many of whom are at the University of Manchester still and were at the time, the agreement between them was incredibly reassuring. So I think I spoke to you a little bit about this spectrum. This is a picture of the spectrum I showed you before, and this is one that I've sort of lifted to show again in my thesis. And as you can see here, this is sort of the point I was telling you about these error bars. If you ignore the very high, the very small, large angular scale measurements, you can see very clearly here, I mean, that one's a little bit, but the following of these data points. I mean, if any of you have ever fitted a line to a curve of data, I mean, it's a nightmare. And that is just like insanely good. And that was sort of really incredible for anyone who was working on Planck at the time, to think that they could get any measurement of just 6 parameters. That's just 6 parameters driving this, 6 numbers to give you this shape. And the assumption of the Big Bang model and get that precision was astounding. And so, yeah, Planck has been lauded as basically the cosmological benchmark. Now, anyone who does anything with galaxies, with gravitational lensing, surveys of all these galaxies, anything, it's all benchmarks against this now. There are certain people who disagree with Planck, but on the whole, everyone just goes, no. The analysis is transparent. Everything's been made publicly available now. We know that Planck has done an incredible job. But I'm not being paid by royalties by Planck. I just love it, just to let you know. And then, so this is sort of the future. So I've already talked to you about an example of the CMB being measured from the ground. That was, Penzias and Wilson did that. And there's been several since then in the 1960s. In fact, several really cool experiments where your radio and microwave signals are less filtered out. I'm not talking about CFHT lens here because it's a little bit of a different mission. But there are lots of places where these signals that come in can get filtered out, and particularly these two, the Atacama Cosmology Telescope, which is in the Atacama Desert, and the South Pole Telescope, which is at the South Pole in Antarctica. They both have, when you have the scan at a particular time, they both have like absolutely unparalleled lack of radio noise coming in. So they're measured from the ground, and they get what we call the small angular scale, which is to the right of that spectrum that I showed you. And when we combine this Atacama telescope with several other sites that are going to be built in the Atacama as well, there's this thing called the Simons Array, which is currently being tested and will be gathering data as we speak. And that is now made into something called the Simons Observatory, which is named after the key benefactor and previous physicist Jim Simons, who is now American multi-billionaire mathematician guy who totally like bankrolled the whole thing. And this is their large aperture telescope, which is currently located on site in Chile. This is a part of the team surrounding one of the dishes, I believe. I can't remember if this is the LAT or the small aperture, the SAT. This gentleman here is my friend Gabriele, who is an Italian currently working out there right now. And he's been oscillating between Atacama and the South Pole telescope as well. So he's actually been out to Antarctica. I'm very jealous. But yeah, so this is really cool. And this is going to give us, this isn't going to be like, oh, this is better than Planck, right? We're now getting to the point where what these little missions, well, not little, these missions start to complement each other and build on each other. And there are things that Planck maybe struggles at the smaller scale of things, that the Simons Observatory is going to be like basically setting their own definitions of how good they are on these scales. So their knowledge of dark energy, their knowledge of the structure formation and the structure of galaxies in the universe is going to be totally unparalleled in terms of ground telescopes. Okay, so yeah, that's everything I've got in terms of the modern advances of telescopes. Now I want to talk to you a little bit about a subject that is closer to what I do with regards to a process which I'm going to talk about called recombination. And it is the consensus that the CMB's best friend is actually atoms. And more truly that the CMB couldn't exist without the atoms around it. Okay. So this is, I drew this graphic up to sort of do a sort of cartoon explanation of how recombination works. So this first slide over here, on the left is a scenario where the universe is very young and the protons and electrons are flying all over the place. They're very erratic, very chaotic, and the energy is very high. Okay. And every time an electron jumps in with a proton, one of the photons or one of the light rays from the CMB will immediately liberate that electron. So as soon as an electron thinks it's got comfortable in an orbiting around a proton, bam, it's immediately liberated by a photon. The light, you can think of like any type of high energy light particle, like a gamma ray or an X-ray. It effectively just ionizes that atom. It strips it of its electron. And this will happen millions and millions and millions of times over millions, if not billions of, thousands of years. Until eventually what happens is the universe itself is obviously expanding. And when this happens, according to the laws of thermodynamics, eventually this net space that everything can fill is getting larger and larger. And usually when we talk about thermodynamics, that generally tends to mean that everything starts to cool down. And the way that cools down is that the photons, as the space gets bigger, they get redshifted, a little bit like what we were talking about before. The space between them gets bigger and bigger and bigger at an alarming rate because of this expansion that's going. So as that happens, the photons get more and more less and less energetic. And when that gets to a tipping point, they try to kick the electron out of the atom. But instead of kicking the electron out, they might move it to a higher energy state, or they might just not affect it at all, but the electron won't go anywhere. It will stay within the atom. And eventually these photons get so weak, they can't really move the electrons at all. The electrons stay orbiting the protons, and you have very stable, the very first hydrogen and helium atoms in our universe. So this process, A to C, you can think of as a snapshot of when we get our first hydrogen and helium atoms in the universe. The colloquial term for this process is called recombination, and it was the bedrock of everything I did in the University of Manchester. Everything I did was surrounding this process. And when that happens, the atoms are closed off. They shut the door on the CMB, and instead of being absorbed, the CMB can't really scatter. It can't really do anything. And so the light, when there's nothing obstructing light, there is nothing for it to do but shine out. And that means in every direction, equally and opposite in every way, the light just shines out until 13.7 billion years later, it arrives on this planet. Okay. So that was the moment that many people will sometimes referred to as the production of the CMB light, is when this happened and these photons stopped bouncing around and getting absorbed and emitted and absorbed and emitted. Since then, there have been things that have absorbed and emitted parts of the CMB, but that's another talk. The most important point is this was where what we see as the cosmic microwave background started traveling across the universe. And we can quantify this on a graph, and this graph is really bringing back some trauma for me because I saw it for about 5 years. But the most important thing, the only thing you need to worry about is the fact that on the right-hand side, this XE tells you how many, it's a fraction, okay? And I know it goes above 1, don't ask me why, maybe that's a question at the end. But it's a fraction of how many of your electrons in the universe are actually just free doing what the hell they want and not tied down to a proton or an atom. So as this is very high, it means your electrons are very energetic and they are just flying around, bouncing into particles and bouncing out again and all this stuff. And then eventually they get to a point where they get the energy gets so low. And this Z is redshift, which as it goes up, time gets closer to the Big Bang. And so as time goes, as redshift gets smaller and smaller, AKA time goes on, eventually these electrons get less energetic and they start going, when it goes to 0, it means they're in fully occupied states. They are totally in hydrogen and helium nuclei bound up. And that little colored band there is approximately when we would say that the majority of CMB photons have been produced. And the reason why we say that is because that little band there is when we see, if you were to map that peak on the CMB spectrum to a moment in time, that big large peak, that would map to roughly this time. And just to give you further clarification on what I mean, you can think of all these giant spots. Don't think of them as particles. Think of them as every time you get one of those spots, that's a massive interaction where an electron and a proton have violently collided or have interacted and given off some light. So every one of those little dots is when light has been given off. And so that slide, that little screen is the right-hand side of this graph when the fraction's high. And when the fraction gets lower, it goes to that. Okay. So I'm just going to go back again. That's on your right-hand side of your graph. And when it goes to 0, that's all it means. There's just less, because there's less interactions. There's less colliding events between sort of interactions between protons and electrons that generate the CMB's light. Okay, so that was the process of recombination, which I hope I've explained. If any of you has got any questions about that afterwards, that I'm serious that without going into the finer details, that really is it in a nutshell. But I can talk to you about it a little bit more later. I'm very conscious of the time. I'm going to briefly shoot through what we've done at Manchester. So the first thing that I looked at when I started my PhD was how if we change electricity and magnetism in the early universe, so if I changed the laws of electricity and magnetism, what would happen to the cosmic microwave background? Theoretically, what would we technically see? And if you actually increase the strength of electricity and magnetism, which is, it's quite sad to see 2 years of your life boiled down into one sentence, but that really is it. Okay. And one graph, by the way, everything just shifts to the right. So everything happens earlier. So everything we think we'd be seeing in the universe would have happened several million years earlier. That's really what would happen. And this is what would happen to the cosmic microwave background spectrum. So don't worry about this alpha thing, but basically as the line goes from green, red to black to blue to purple, you can see the trend here, right? It's shifting. And the reason why it's doing this is because it's moving to the smaller scales. So the ruler's getting, the higher angular scale, ruler's getting smaller and smaller and smaller. And the amplitude's going up. So the differences between those two temperature spots is getting larger and larger. And if we were to see this in real time, imagine if we could have like thousands of universes all superposed on one top of one another, it would look a little bit like this. So it might be hard to tell because I think it's hard to tell, but I don't know if any of you can notice that actually the yellow is starting to get more and more intense in this map, but the dark blue is also getting more and more intense. So when you start, you see there, it's sort of like fuzzy green and the differences are slightly closer to each other. But as we increase the strength of electricity and magnetism, we actually make the deviations higher and higher and higher and closer into these much, much larger temperatures and much, much lower temperature differences. And so that's really what we would do to the universe if we completely broke electricity and magnetism and made it really much, much stronger. And so I did quite a lot of work on that. I then spent a lot of work working at, you know, rather than sort of picking a model, cherry picking models, what would happen if we backwards engineered it? So for you, this is probably the most quantitative I'm going to try and get today, but so I'm going to try and fly through this because if you want to ask me questions, ask at the end. But what I did in this simulation here was I said, right, let's inject a load of energy to our electrons at different times in the universe, where here is closer to present day and here is, say, about 100,000 years after the Big Bang. So I've concatenated the whole universe's timeline roughly onto this line. And I'm going to give a kick at every different time. And eventually you'll see from this that at some point, this graph goes a bit crazy. And what that is, this is the difference in the cosmic microwave background spectrum. So when this starts going crazy, it actually tells me that the CMB's differences are largest if I kick a load of energy in at this particular time in the universe's history. And that's good because that is the most important part of this entire analysis in terms of time series. So I don't have to worry about all these times where nothing's happening. Theoretically, I should be saying to everyone in cosmology, actually, you're only interested then in that particular time band. And that was so this was a part of an analysis method, data analysis method called principal component analysis. And I think I've left out the big plots here, but it was just really nice to see how you could change how the electrons scattered in the early universe and see how much the impact would be if this happened at different times. And yeah, I can talk about this a bit more if you want me to, but that was sort of the second part of my PhD. And then finally, we get on to this, and I will finish as quickly as I can on this particular topic. So spectral distortions are a really important field of interest. And to kick off, I've got this slide, which is very dense in information, so I'll try and whiz through it. The spectrum that I showed you here, right? I think you remember me saying it's not quite perfect, and I said I'll hark back to this at the end, right? So if you actually measure what the wiggle, so what this would look like theoretically versus what the data actually or shows you compared to a black body, which is a perfect emitter, mind you, right? You actually get these little wiggles here. And sorry, away from the microphone. So these wiggles are called spectral distortions. And they tell you that whatever's going on is not quite as thermal as you think it is. And the reason for these different shape, they look very similar. You can probably tell they're slightly different depending on what time they happened. So higher redshift means earlier. This is the Big Bang. This is today, right? And the difference actually tells you about many different physical phenomena that we don't really fully understand yet. And it's quite a lovely coincidence that the physics that we don't understand tends to be filled out by a lot of spectral distortions. And yeah, these tiny fluctuations. This is sort of the front line of cosmology right now. There are lots of other areas of cosmology that are currently getting a lot of funding and getting proposed as well, but I'm not going to talk about those. They're not the area I'm on about. This is spectral distortions is the area that I've been on several proposal bids for. And ESA are currently working through several candidates for the next big mission. And this New Horizons in Cosmology proposal, which the research group, the Spectral Distortions Group at Manchester are tantamount to building, we're sort of currently invested in trying to get a satellite up to measure this particular signal. And this signal here is the one that I was most interested in while I was a postdoc at Manchester. And the reason why I'm so interested in it is because if you remember, I spoke to you about recombination physics. Well, recombination, the process of atoms and photons sort of doing this merry dance, right? That isn't totally thermal either. That's not perfectly thermodynamic physics. There's some imperfections in there, which is what the spectral distortion is. And you can actually tell exactly where the non-thermal is happening in the hydrogen and helium atoms from the peaks coming here in this recombination signal. It's a very unique signal. It's very, it's understood, but it hasn't been studied very much yet. This is from a coding package that my PhD supervisor, Dr. Jens Kluber, who a lot of my work has done with, he developed this, the first one. And the measurement of this will effectively, if we can get a good enough precision, cement any sort of misgivings we thought we had about the standard picture of cosmology. Because what I failed to mention is that our current understanding of CMB means this has to happen. This has to be there. It's just very small. So if we can get a satellite that is strong enough, or shall I say has the sensitivity to measure this, this will give us an entirely new way of measuring cosmological parameters. The caveat to that is we still need to build something that sensitive and we're a little way off. But that is, I'm not being blasé or romantic when I say we aren't as far off as you would think, and people are ongoing building these things right now. There are people as part of the Indian Space Agency are building ground detectors for this. ESA have the proposal for something called the Voyage 2050 missions, which we've been an active part of. And now NASA have started to put out their calls for proposals as well, which actually I was, even though I'm not in the University of Manchester, they put my name on the proposal, which was quite nice. So yeah, these things, this is a really, really, really top of the line sort of studying area at the moment. This is just a demonstration of a mission that NASA was hoping to put out, called Super Pixie, which was sort of like going to be a pathfinder for this new mission, Voyage 2050. But again, there's so much interest coming from the cosmological community about these distortions right now that eventually there will be a telescope like this one built, and it will be a lot better than this. So I think I've taken up enough of your time. I will conclude by saying it has a very storied past, the CMB. I've told you already, it's quite a comical story and it's quite wonderful. It redefined everything we thought we knew about cosmology and the accuracy of the things that made up our universe. Completely redefined what we thought was good cosmology, and every other area of cosmology is currently trying to get to where we are with that. It is still being investigated today, and modern advances in radio astronomy, telescopes, and low temperature physics are being driven by the motivation to get a better measurement of the CMB. And I think that's really cool because it brings all these areas of physics together, as astrophysics often does. And these spectral distortions probes will unravel theoretical, unravel theoretical physics ideas that we'd ever thought in our wildest dreams we'd be able to do within like my lifetime. And that, I think, is one of the most exciting things about the CMB science to date. So I hope I haven't bored you. Thank you very much for listening. I know it's been a long one this evening and probably a bit of a slog, but I am happy to answer all the questions you have. Thank you very much. Lights.
We'll take some questions. We'll get
Lights.
some lights.
Light's going to shock me.
Okay. Wow. Thanks, Luke. Thanks. We're going to take some questions now. Can I start? There's one telescope that I was waiting for you to say.
No, yeah, I never get all of them.
And you never mentioned it, the James Webb.
Yeah, I heard it dotted about at the start of the talk, and I was like, "Is everyone going to expect me to talk about the James Webb?" Yeah, so I've actually spoken several times. Well, I haven't spoken several times. I've spoken before about the CMB on a much smaller degree, and someone asked me about the James Webb, and I was hoping you weren't going to ask me about. So the James Webb, I mean, I'd be naive to say it isn't awesome and amazing and one of the most exciting parts of astrophysics right now. Unfortunately, the problem with the James Webb is because it's focused on the infrared bands, it's not really going to tell us very much about the cosmic microwave background. But what it will do is it will give us another layer to how we understand the early universe, sort of, where you remember I told you all about the reionization and how poorly understood that is. James Webb is, when I talked about SKA in here, I should have really given James Webb the credence. That will be able to get the very first galaxies, whichever basically formed. And the timing of these galaxies roughly gets close to the very edge of the reionization epoch, which is sort of it's not high redshift in terms of the CMB, but it's high redshift in terms of anything you could see with a bare telescope, which is absolutely unbelievable. So for the purposes of complementing CMB science, the James Webb is going to be really important. Unfortunately, it's not going to be able to tell us anything else about the microwave sky. Exactly. But yeah, I'm very excited for what it comes out with, because anything that can, I mean, I find reionization as a topic very fascinating. And the CMB, actually, I didn't say this in the talk, and I should have, to be unbiased. CMB can't really tell us very much about reionization. It's quite desensitized to it. So we put it as a parameter because there's a certain way it affects the spectrum, which is unique. But we really need better probes, and the James Webb should hopefully fill part of that void.
Nice.
Without the play on words.
Okay.
But yeah.
Thank you. Thank you. Any questions from the audience? Yes, Gerard?
In the formation of helium, first helium, where do the neutrons come from? Sorry, no. Yeah, this from my side.
Yeah. So sorry, so just to check, are you asking me or do you know? Because if you know, that's awesome. Okay. Yeah. 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 So the question was the Holmdel-Horn antenna, which Penzias and Wilson used to discover the CMB. What current? Apparently, it's fallen into a similar state of pigeon poo. And is it being preserved? Unfortunately, the answer is I don't know. So, and I should know. So you've outed me. But yeah, unfortunately, I don't know. But yeah, I mean, it really should, shouldn't it? It should be preserved, because I know Bell Labs were taking. So when I last read about it, I think it was in New Science a few years ago, because they were doing a little bit of a discussion about it because the last Planck results came out. And obviously, when you talk about the CMB and Planck comes out, I think they wanted to talk about the history a bit. And Bell were definitely trying to look after it, whereas what you've said now completely undermines that. So obviously they haven't been doing as good a job as they should. I don't know, but the answer, yeah, the honest answer is I don't know. I hadn't heard that story. So yeah, we need to find out. You need to tell me.
Gerard will let you know.
Yeah, good. Yeah.
Dave?
Oh, sorry.
Oh, go on, sorry. Yeah.
The fine structure constant, yeah. It's a fantastic question. So the question was, what was the motivation for looking at the electromagnetic constant, which is, in physics, we call it the fine structure constant. Yeah, the gentleman I spoke to was talking about solid state physics earlier, so I definitely understand why that would underpin a lot of the work in solid state. So you can actually, by accident, I don't think, you can study them both separately. So when you're looking at gravity and modified gravity, you can look at it as a sheer measure of how strong gravity is by rescaling Newton's constant. And you can also use modified gravity frameworks, which are very, very dense theories, which even I wouldn't be comfortable giving a lecture on them because A, I wouldn't do them justice, and B, I find them very, very dry. It's a topic it's not particular, but it's very cool to hear about. The fine structure constant specifically doesn't tend to tie in the way that gravity does. It's purely does in the sense that because it's a fundamental force of nature, you can try and alter the magnitude of how strong and weak it is. So the reason why we looked at it was because recombination itself is an electromagnetic process. Everything relies on the electromagnetic force, and how strong, basically, I realize I'm going down the rabbit hole here, how strong electricity and magnetism is on different scales. And originally we did it to demonstrate how the microwave background would change under these particular circumstances or environment where that constant was different. In the last 2 years, it's opened up a whole can of worms where a group in Pennsylvania and several people who I know in the University of Cardiff and in an Italian university, I can't remember where it was, and then Turin, and a friend, Professor Carlos Martins, who's in the University of Porto, they all found that there's several theories of very, very high level theoretical physics, particularly related to string theory, where the fundamental constants, fine structure constant alpha, the strength of electricity and magnetism would vary given this particle that is given rise from string theory. So that's been ongoing for a few years, but when we were doing our studies, we weren't really aware of that. But as I've gone to do more work on my PhD, I had to understand the context, because the biggest question that I get asked, and you asked it in a very diplomatic manner, but most people will ask, why bother? And they'll say it in that way, right? But the truth is, we were just trying to experiment with what would happen if that was different, because the fine structure constant is measured so precisely in the lab, but what we're actually doing is measuring it 300,000 years after the Big Bang and trying to find a motivation for that to change. And there are theories that say that this could change, and that would totally open the lid on all of what we think about theoretical physics. So yeah, it's that's the motivation really. But yeah, I hope that was a good enough answer.
Thank you.
I think Dave, you're waiting for a question, yeah.
During the first half, you got quite excited when you mentioned dark energy.
Yeah.
And obviously an interest in yours.
Yeah.
I get asked by members, what is dark matter?
Yeah.
Dark energy and dark matter.
Mhm.
What is the difference in what is the dark matter?
Yeah, so the question is, what is dark energy and dark matter, and what is the difference? And it's a very it's the litmus test for cosmologists being able to answer this question, to be honest. So so dark matter, I'll start with dark matter because it's slightly easier. They're both quite difficult. It's a slightly easier one. Originally, when we looked at galaxy rotation curves, so we would look at galaxies and we look at their redshift and how the light changed, we would see the light on different parts of the galaxy blue shifted and red shifted, and we'd see them spinning, right? And when you look at the center of the galaxy and you move out, you can measure how fast the galaxy is rotating, okay? And yeah, just trust me on this one. It does work. The problem is, majority of physics, we tend to assume that anything to do with space in the first instance behaves something called Keplerian, which means it obeys Kepler's laws and it obeys Newton's law of gravitation. So what we were expecting to see, and I'm gonna have to draw this with an imaginary line, is we were expecting to see something that went up and then went down like that. But what we actually saw when we looked at galaxy rotation curves is it went up, and then when we got to the edge of the galaxy, as we went further out, it just sort of go flat. And that really sort of threw everybody off, because it meant that the speed that stars in the outside of the galaxy were moving just as fast as ones closer in. And the only credible explanation for that, there's been several, but the only credible explanation for that is that as you get further and further out, the amount of matter in your disk, in your galaxy, gets larger and larger. The problem with that is when we look at these galaxies, no sign. And so that was the first that was the smoking gun for this type of matter that we think must be there because of the gravitational impact, but we can't physically see. Now that's very localized example of dark matter. But on the larger scale, when you extrapolate that to every galaxy in the universe, that's a hell of a lot of matter that we can't see that is actually accounting for quite a lot of what's going on. And using the CMB and using also a very important tool is something called weak gravitational lensing. So we can look at a galaxy and then we can look at how the light from a further galaxy, as it comes and it passes anything that's got any like serious mass, the light will be bent around. And instead of looking, and this again, sorry, my imaginary pen, but if you, instead of having something that, maybe I could use a clicker, maybe that would work. No, that's going to be just as rubbish. Right. Okay. So instead of having something that looks like this, it looks much sharper and the ellipsis gets thinner. Now that doesn't sound like a very big effect, but when you map that across the sky, you can measure how strong the intrinsic signal is from the galaxy. And you can measure, you know, there's something in the way because you can see because of the galaxies all orientating themselves. And so you can then use tools like this to map exactly how much matter is in the way that is warping the light of these galaxies. And that will give you a rough, what we call a tomographical map. So as we look out, we don't see, but we infer a distribution of matter that gets in the way. And we can't see any visible light from this, but we know because it's bending the light around from distant galaxies, there must be something there. And that really, when you take in gravitational lensing and the cosmic microwave background, we predict that of all of the matter that we see, sort of over 90% of it is 95% of it is dark matter. So 5% of total matter is made of visible matter. Okay, that's one answer to your question. So the second part is that I've just told you that the majority of matter is dark matter, right? But even matter, dark and visible, makes up 33% of our universe's total content, because the other 67% is something called dark energy. And dark energy was originally theorized by Einstein to be the thing that pushes our universe and makes it expand faster. But we've started to notice that dark energy, it can't just be a mathematical fluke to fix Einstein's equations. It must be there, because not only do we see it in something that is driving the expansion of the CMB would effectively be slowing down. If there were nothing to dark energy, it would be like, if you think of an explosion, when something goes out, eventually everything starts to sort of dissipate in the edges. That's not what's happening in our universe. It's getting faster. And the only way that could be accounted is if there's some unknown pressure pushing everything out. And the scale of that pressure, if we were going as a constant, the amount of matter would be equal to the dark energy. If it were slowing down, the amount of dark energy would be less than the matter. But because it's getting faster, we know that there must be more dark energy than matter, and the figure is 67 to 33. So to answer your question, dark matter is a substance that we can't see, that we don't know very much about, and there are still particle experiments that I'm not 100% convinced of, but are trying to determine what particles make up dark matter. And dark energy is this unknown random thing pushing the universe out. That's it. Dark energy is really fast. Yeah. Exactly. Yeah, dark's a misnomer. It just means that it doesn't do anything. Yeah.
We call it that because we don't really know what it is.
No, yeah.
I guess it was just a name that someone thrown out there as the Big Bang.
Precisely, yeah.
Oh, and that was a bit of a mock.
And my when I started at the university as a master's student, as I was halfway through my master's, I did an internship with quite a formidable cosmology. I'll say this on camera because I know him and he knows that I respect the hell out of him. Formidable cosmology professor called Richard Batty. He's still there at Manchester. He's fantastic. I honestly, I get on very well with him. And one of the things he always says in any lecture is anyone who visualizes the Big Bang as an actual explosion, he gets very angry about it because it's not the way it worked, but because of the way it's named, that's everyone visualizes like that. So yeah, unfortunately, naming conventions tend to sometimes lead you down the wrong path, even though they are better named than what they actually do. So yeah. Yeah, no, you're welcome.
Any more questions from the audience? Yes, Gerard.
Jim Stacey, isn't he? Right. Jim Stacey. That's
There we
right.
go.
No, waste of time here, aren't we?
Oh my God. So it didn't have more pigeon poo on it. Probably does. Yeah. Cool. So just to the people on Zoom, the Homdell is fine. The antenna is safe. It's all good. Being protected. Cool. That's amazing.
Are you okay to take some from Zoom?
Yeah, absolutely.
Or any more questions from the audience?
Yeah, please don't be shy.
Right, Jim Stacey.
Can we go to Zoom now?
Jim Stacey's got a question.
Mhm.
I don't know what it is. Could you ask Jim to read his question out on my phone?
Jim, Mark has asked kindly if you could read out your question to Mark on Zoom, and then he'll read it to me, if that's okay,
Okay.
please.
Right. When in the early part of the universe, you have helium being formed alongside hydrogen, but where do the neutrons come from?
Okay, that's a really good question. That might have shot me in the head. So helium wasn't actually produced at the same time as hydrogen. That's the first thing. That's a technicality. So helium was actually produced just before. Helium, because it's higher mass, means that as the universe is cooling down, it actually has a stronger electromagnetic pull on the electrons, and therefore the electrons stop resisting the helium nucleus quicker than the hydrogen does. Neutrons. Okay, so if I pitch this too high, I'm sorry. Okay, so the best way I can explain this is if you think of the Big Bang as everything being as stripped apart, fundamental as possible, because the energy levels are so high, you can think that the energy, so just nod, please, because I want to keep you all along with me. Otherwise, we're going to have a long evening, right? And I'm going to need a beer. So if the energy levels are really high, thank you. I thought that would be a beer then. I was really excited. Okay. So if we're at very high energy levels, right, you can suppose that, let's say the Big Bang, it doesn't, but let's say for argument's sake, it goes so high, higher than anything we've ever experienced or could even imagine. That actually is higher than the Large Hadron Collider, okay? The Big Bang is theoretically a point of infinitesimal mass and density squeezed into, nanometers, smaller than nanometers. So eventually, as the universe cools down, particles, you can think every particle that was created in the Large Hadron Collider or an even bigger collider, you can actually think that since the Big Bang, the universe has cooled to a point where that particle that was created in such a high energy environment, okay, would stop being produced because the energy would get too low, right? We don't see Higgs bosons flying around. And the reason why is because the energy is not high enough. So just as a broad stroke, every particle that ever existed that we've ever detected could have existed at a certain energy scale. And the energy scale of, say, tera electron volts, which is a very high energy, is at the point where the light is flying around or the particles are flying around with that energy, means that particles that were generated in the Large Hadron Collider could have existed at that time. And then it gets cooler. Those particles, they clash, they crash. They can't be created anymore because the energy is too low. All right. At one point in that particular story of particles being created and destroyed and created and destroyed, hits a limit where we have something called the quark-lepton transition. And that's just a fancy way of saying the particles that make up protons and neutrons stop flying around freely because the energy is so high, and they start binding themselves into protons and neutrons, where you have up and down quarks forming protons and neutrons. Now, the really weird part about the quark-lepton transition is that up-down quarks themselves, actually, the further you pull them apart, the stronger their force gets. So the idea of pulling quarks apart is actually it's really bizarre. However, the energy levels at those scales are so high that those quarks can physically do that. And to be fair, even in, I'm not going to go down the role of particle physics because I haven't done it since 2015. However, I guarantee it will have, Mark. It will have definitely changed. However, when you pull quarks far enough apart, the amount of energy, potential energy stored in those particles is enough to effectively create a quark and anti-quark pair out of nothing. That's how high the energy is. And that might be hard to get your head around, but that is a fundamental facet of quantum mechanics, is this idea that particles, if you have enough energy, you can generate a particle anti-particle pair. So yeah, in answer to your question, because I believe that we've gone down a rabbit hole here, as you get cooler and cooler, at some point, the quarks that were able to fly around in these very bizarre particle pairs will have had to have collided and crashed and interacted in such a way that protons and neutrons could then form to give us the first bedrock of what we call the nucleons, which are protons and neutrons. For those of you who are well versed in nucleons, you get these things called mesons as well. And you get these other bizarre types of mesons, of which protons and neutrons are part of the set. Every other particle, apart from protons and neutrons that are made of quarks, are so unstable that after less than a nanosecond, they always deteriorate and decay. So that's why we never see them. But yeah, I don't want to turn this into a particle physics lecture. But if you ask me the time, if Jim asks me the exact time after the Big Bang, I will go and cry in a corner because I don't know. Okay. So.
Right. Thanks, Lee. And Jim, we'll expect a newsletter article about how a neutron was formed. Thanks for the next month. Thanks.
I'm
Well,
not helpful for that.
you may not have done it. You may not have done it since
Any more online?
2015. I've not done it since 1962. Probably discovered since then.
Yeah.
Yeah, please go ahead.
It's fine. That was, yeah, that is and was the, well, that is a very big question, but it was a much bigger question until about 56, probably about 60, 70 years ago. I don't know if you've heard of the theory of inflation. And so inflation is this idea that the perturbations, again, inflation is a little bit like the particle physics, is a little bit like dark energy, where it is incredibly hard to explain in like a elevator pitch style time. But inflation was originally sourced as a problem to a lot of other cosmological issues that were going on, and there was something else needed to the Big Bang model. Kind of similar, your question is one of the smaller issues that comes with that. But we need something to have generated the initial perturbations, and inflation is a popular model of this. There's a particle or a particle physics model where you get this particle called an inflaton, which we're going really high level here, as in like I don't know half of this stuff, but it in particle physics we talk about fields a lot. And the fields that define, yeah, exactly that. So the Higgs boson is produced, or the Higgs boson was produced when the particle, the field that defined the Higgs boson can roll down a hill. And when it rolls down a hill, it creates a potential hill, which is an abstract concept. But when that happens, that's the production of a particle in the field. It's a disturbance in the field. And the inflaton, actually, I mean, you've hit upon something again huge, because there is a lot of people who believe that the Higgs boson could be the reason why inflation happened. That's a very popular theory, very, very intense mathematical theory. But the inflaton, as it rolls down the hill and it loses energy, the field, sorry, not the particle, the disturbances that pop up give rise to this particle called the inflaton, or whatever you want to call it. Now, when that happens in the model of the Big Bang, because of the way that field behaves in time and space, it would generally create a period of expansion that would behave like an exponential curve. And for those of you who don't know what an exponential curve is, it looks like that. Okay, so every time you go up a step, you're basically going up a step. It's like power to the x mathematically. I don't know how to describe it in layman's terms. You're solid state, you should know. How do you explain? You need to know. I know. It's really hard to grasp and explain it in a way. Yeah, that's a great analogy. I'm going to use that. Yeah, so sorry, let me try and bring this back because I've gone a bit further off piste. Yeah, so that generated an exponential, huge period of very, very violently quick expansion in the universe's history, much quicker than anything else that has happened since the CMB was generated, and even before, when the first nucleuses were first made, which was a lot before. Now, this is the part where a lot of people switch me off and don't like what I'm about to say. And I know because I've had this conversation with Emma and she doesn't like my explanation for this, and it's perfectly valid. But even in the terms of the Big Bang, you always have to have I don't know how to say this colloquially, you always have to have an error. There's always statistical noise. There's always an error. Nothing is ever perfectly perfect. You know, you can never really get true zero in a number. I don't know how to explain this metaphorically, but what I mean is even when the Big Bang was that small, there was a statistical noisy up and down that was happening that was because it was a small signal on a small, there's no way even trying to rationalize it in your head. Okay. But when inflation happened, that statistical like up and down across space was just caught, and then inflation happened and every single one of those little statistical anomalies got blown up. And that's how you get your positives and your negative perturbations. So inflation isn't the thing that gave you, it just amplified, exactly. And that's how you end up with these ripples. And it's wrong when I say ripple, because that infers that something caused the ripples. It's not. It's a statistical anomaly that had to be there, subject to the laws of nature. We know laws of nature have to have imperfections everywhere. And even this tiny, tiny, tiny imperfection, because of the way inflation worked, it just blew them all up. And that's how you end up with those first perturbations.
Okay, thank you.
Sorry.
We're going to have to we have to be out by 10, and we've got to tidy up as well.
Sure.
If there's no more questions on Zoom, we'll round it up, and I'll ask Mark, please, to give us the vote of thanks. We don't let you leave without a vote of thanks.
Yeah, so thank you so much for coming to talk to us tonight. I remember when that first image from COBE came out, I think it was like the mid-90s.
Yeah.
And I was just doing my GCSEs, and I was thinking about, I'm going to go to university, do astrophysics or cosmology. It's amazing seeing the detail in the images that you've been studying and that are being released now. You know, instead of these big blobs, you can actually
they look like a Mario Kart game, like a Mario game in the 90s, didn't they? I know what you mean. Yeah.
It's really great that there's people studying this stuff and teaching us more about what happened back then. In the times that we can't see with an ordinary telescope. You mentioned about your graph, you're boiling down years of your life into a single graph, but I always remember something, I can't remember which scientist it was said it, but it was in physics. There's a sort of general rule of thumb that the simpler your equation looks,
Mhm.
or the simpler the graph looks,
Mhm.
the more beautiful the mathematics
Yeah, that's
is,
very
and the
true.
more likely it is to be right
Yeah, that's very true.
instead of all complicated things.
Yeah, yeah.
So well done. Thank you so much for
You're welcome. You're more
talking
than
to
welcome.
us tonight. I
No.
hope we can get you to come back.
Yes, it was a pleasure.
Thank you. Can we have a round of applause?
Thank you. Right, I'll go away now.
Right, thanks, folks. That's all there is. Just left to tell you when the next meeting is. Date of the next meeting is Friday, the 22nd of April, in here, hopefully, subject to any COVID infection rates preventing us coming back again. But if not, we'll be here on Friday, the 22nd of April. And just bear in mind, that's not the third Friday, because the third Friday in April. Oh, yeah, sorry. So, sorry, I'll say that again. The date of the next meeting is Friday, the 22nd of April. And just to make you aware that that's not the third Friday, because that's Good Friday. So it's the following week, it's the 22nd, okay? And thank you for attending, and safe journey home. And thank you to those people on Zoom and YouTube for watching. Thank you and good night. Meeting closed.